Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Leveraging RISC-V as a Unified Heterogeneous Leveraging RISC-V as a unified heterogeneous hardware and software platform for next-gen AI chips. Brought to you by Tech Online, Akeana, and broadcast by AspenCore. I'm Colleen Heckman, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. At this time, we recommend you disable your pop-up blockers. You may ask questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then hit the submit button. If you're experiencing any technical problems during the webinar, you can type that issue into the Q&A text area, click the submit button, and we'll be glad to offer one-on-one assistance. I would also like to encourage our attendees to complete the feedback form that is located on the right side of your console. Please be sure to complete that form before you log off today, and thank you in advance. And now, on to the presentation, Leveraging RISC-V as a Unified Heterogeneous Hardware and Software Platform for Next-Gen AI Chips. Discussing today's topic are Graham Wilson, Head of Products, Akeana. Graham has over 25 years of experience in the semiconductor IP industry, with 15 years in processor IP working at companies as Telesinca, Cadence, Synopsys, and Sci-Fi. His main area of focus has been DSP, vector processors, with recent focus on AI computation processors. And joining Graham today is Dr. David Baker, Lead AI Architect, Akeana. Dr. Baker received his BS-EE from NMSU and his MSc and PhD in ECE for the University of Texas. He's had a long career in the industry at TI, IBM, and Rockwell, and other startups. He has spent the last 7 years working on hardware and software for machine learning acceleration at places like ETA Compute, Luminous Computing, and Akeana. It's with great pleasure I now hand things over to Graham to begin. Graham, take it away.
Thanks, Colleen, for that wonderful introduction. Hello, everybody. My name is Graham Wilson, and I will give you the first part of this presentation about Akeana AI solutions. To start off with, I'll talk to you about the company, Akeana, which is a processor IP company. So the company is fairly new. It was founded about 4 years ago. But the engineering team that's the foundation of the company has been together for around almost 20 years. They came from Cavium Networks, then Marvell, and as a team, they developed the server chips using ARM processors, but developed the processors for multi-threaded architecture. And they really built up a very strong expertise in processor design, but also chip design and interconnect of multi-core processors. So when they came to Akeana, founded Akeana, and then targeted the RISC-V instruction set architecture, they were able to very quickly build up a single design database, which enabled the building of a broad range of processors and system and interconnect blocks. Another key point about Akeana, as I say, is the single word that defines Akeana is performance, performance, performance. The first part of the performance is in the cores. Akeana offers leading edge RISC-V performance processors that have a leading 25 spec int per gigahertz score. But also performance in terms of interconnect infrastructure and scalability of multi-core systems. And then we'll go through on the third performance in terms of the data movement and support of parallel processing. So for the Akeana processor IP, we have 3 different product lines which are targeted towards different applications. And each product line will have multiple different cores. Starting with the Akeana 1000 series, which is 32-bit, comparable to ARM Cortex-M and Cortex-R. And then the Akeana 1000 series, which can be in order or out of order for consumer automotive-like applications. And then we go to the Akeana 5000 series, which is the ultra high performance, 6 wide, 10 wide issue out of order architecture, giving leading edge performance that's comparable to ARM, Neoverse, N2, N3 class of cores. Another point for this webinar that we'll go through, the Akeana 1000 and the 5000 both can be vector extended, can add AI acceleration instructions, and also support multi-threaded support up to 4 threads support. Before going into Akeana AI solutions, I just wanted to highlight the point about the momentum that RISC-V has built up in AI solutions. There's been a lot of good design wins with RISC-V cores. Big tier 1 customers like Google, Meta, and NVIDIA have announced their adoption of RISC-V in their AI solutions. NVIDIA gave a presentation at the RISC-V Summit about using RISC-V cores. And in a way, you can summarize it as 2 key areas that RISC-V offers that are strong for AI. First, on the software, with the standard ISA across multiple heterogeneous cores, and as well as the software ecosystem. So building up the software support, all of the models, the libraries that can be optimized and upstream, really simplifies the building of AI-specific systems and software stacks. And then also on the hardware side, the RISC-V vectors. So AI computation is very data intensive and sequential, so can really benefit from vectorization. And so vector support that is offered with RISC-V, there's the RISC-V vector standard that is being ratified and frozen. And a lot of the IP vendors, the RISC-V processor IP vendors, have implemented that. And also because of the flexibility of the vector standard, it's kind of compile once, execute multiple times. That leverages code across multiple different vendors or different cores, so very flexible. And also the ability to add custom instructions. So the RISC-V ISA standard allows for custom instructions, and either the RISC-V community or different IP vendors can add custom instructions that greatly accelerate different parts of the AI computation chain. Now, let's focus on what Akeana, as an IP provider, can really offer and enable its customers to lead in AI computation. And that's really our focus. So when we look at the AI solutions and the requirements of customers, clearly there is a broad range of applications, there's a broad range of computation requirements. And AI is not a single processor solution. It clearly has become a range of processor solutions to meet this wide range of applications, different performance requirements. We're also seeing that there are different trends in terms of the architectures. So there's a traditional GPU architecture that has then evolved, and Google then drove into the TPU. We also see language processing units, which the LPUs, which have further customized and use more heterogeneous architectures for the processing of large language models. And we're also seeing trends moving towards we're trying to overcome the issues of data movement and the bottleneck that this is becoming, where we're seeing trends in moving compute closer to the memory architectures and dividing up computation. So when Akeana needs to address the processor and the IP requirements to enable our customers to really take leadership for AI compute, it's clear that we need to offer the broadest range of AI optimized high performance compute and also high performance data movement IP. So from Akeana, we want to address the more complete computation domains. And we see that there are 2 types of the computation domain areas. The first is what we call the general purpose compute array. And this is more sort of your front-end software computation, executing applications, parts of framework. It's generally a scalable, homogeneous multi-core system. You'll be running frameworks, allocation, task management, synchronization. The second part that we are addressing is the AI accelerated compute array. This is what more your traditional, you'll be thinking of like AI accelerators. And this is a highly optimized heterogeneous system with multiple types of compute engines as well as data movement engines that are connected in a highly optimized framework fabric for performance in terms of compute as well as data movement, really focusing on highest compute per watt efficiency. And then by focusing on both of these compute arrays, we can also offer a more unified AI software stack across general compute as well as AI accelerated compute. So the hardware is both of these hardware compute arrays are supported by unified tool chains, unified debug, so consistency of debug, profiling, testing in this single hardware platform. We also have possible reuse of code, library routines, optimized code for various different algorithms that if the customer wants, they can move across from one compute array to another if they need to meet future-proofing computation requirements. And this can give kind of a unified performance, power trade-off. Do you want to run flexible operations on the compute array, or do you want to run them on the more optimized acceleration AI accelerated array? And this is supported across compilers, LLVM, and library kernel routines with neural network frameworks, as well as Linux OS support that you could be running across the general compute array. Or if you wanted to build that into the accelerated compute array and run an OS, you can do that as well. So let's look at the CPU general purpose compute array and some of the trends that we are seeing and future requests that we are getting from customers and what Akeana can do. So first thing is that the traditional model of just a CPU running as a host kind of is changing because the AI compute models and the trends in AI computation is really pushing to more capability within this general purpose compute. So we see the requirement for multimodal models. We also see AI agents coming in and the computation requirements of these. And this is kind of pushing a change in the traditional model of just the host running to and then running on the AI accelerated and more sequential, that AI computation is becoming more dynamic, more bursty, some more decisions need to be made, branches need to be taken and so forth, which kind of pushes some of the computation onto this general purpose compute array. So as needing to meet those requirements and fulfill that need, really the Akeana 5000 series really is an ideal solution for this general purpose compute if you are looking for an alternative to other CPU architectures and you want to look at a unified ISA across host and AI compute. So Akeana 5000 series are ultra high performance, 6 to 10 issue wide, out of order cores. These are vector extended, and we can add AI acceleration instructions so that if you want to offload some of the requirements and push them onto the general purpose compute, you can do that. These cores are very high quality, enterprise class CPU with high security, RAS features, as well as telemetry features, and then also the interconnect. So we offer with Akeana Mesh, coherent core coherent interconnect in a 2D fabric that supports Amber Chai, so will allow you to scale the number of cores to meet whatever computation requirements that you have. So for this slide, showing Akeana as the leader in core performance, I took a slide that was shown in the RISC-V summit in China last year, and it was put together by a third-party person who really took all of the performance cores available at different years and then plotted those, as well as including processor cores from various different SoC implementations, pulled that together and showed a trend in terms of the performance improvement over time with reference to industrial standards spec in 2K6 per gigahertz score. And it showed that in the future, the breaking the performance barrier of the 20 score. And then I'm showing at the points that the Akeana 5000 series, our ultra-high performance, really offers leading-edge performance with up to 25 spec int for the Akeana 5300 core. Another point to state is that these cores are available already. Customers can license, evaluate. We offer a broad range of emulation and simulation platforms for customers to then bring in to simulate performance of these cores and use them. Last year at the RISC-V Summit in Santa Clara, we actually showed a demonstration of the 5100 core running in a Synopsys HAPS platform it was running an OS, Linux OS, as well as hypervisor functionality. Okay, so now switching gears a little bit and moving over to the AI accelerated data compute. So as I said, this is really focused on sort of optimized compute per watt, heterogeneous cores. So breaking down what we see as the main key processing elements within this data compute array. So starting off with what I call the AI control core. And this is kind of like a front end, can be performing all sequencing, task allocation, can be supporting multitasking, data management. And this is capable of running an OS, maybe an RTOS, sometimes even a higher OS such as Linux and so forth, depending upon the applications. So this kind of provides that high-level software front end, but it also can be implemented and used in the AI computation flow itself. So some of the tensor formats, some of the pre-processing, whether it's ETL pre-processing and so forth, as well as if some of the functions that get used in the transformer models can be implemented on this core. So the vector compute capability is added with some AI acceleration if needed, and then also multi-threaded execution because it's dealing with possibly multiple executions, as well as resource management, interrupt support, and so forth. And then the next main part is matrix acceleration. So, I mean, everybody knows maybe 50% of the computation workload is on matrix computation. And so offloading this to a dedicated MapMul engine clearly makes sense in compute per watt. This area, plus we know that customers have their own implementation or want to bring in their own matrix multiplication accelerator. Another area is what I call the AI processing element. And this really is, you think about it as a vector computation beast, very wide, kind of a little bit limited in terms of the tasks it performs, but it's really key elements that need to be that offer the best compute per watt for various different vector computation. And this can be run in what I call a data pushed mode, where it's kind of like a slave. The data is pushed into the local memory of this core. Once it's available, it then processes that and then notifies the system that the operations have been complete. Generally, these are fully cycled deterministic operations. They can be running out of closely coupled memories. So once the data is pumped in, the result is then available in a fully deterministic n number of cycles later. And then the data movement. This is key. It's okay to add compute, but that's not really solving the bigger problem. The data movement is the issue. So we see data movement engines, flexible data movement engines. I call it an AI data movement engine. Multiple channels, the support of parallel movement, as well as AI computation functions integrated. So when the data is being moved, it's also being modified for whatever functions it needs. And then there's also the data interconnect fabric. It's not just having the cores and the data movement. You need to have the fabric that's highly optimized to give peak data movement, parallel operations, that gives these data flow channels, that meets the compute needs. So you can have all of these cores running in parallel, and then the fabric to support that and providing and taking out the data. So Akeana meets the needs of these various different types of AI computation and data movement cores. And we did this by leveraging from the Akeana 1000 series core, which is an in-order pipeline 64-bit vector extended with various types of memory architecture, caching, or SRAM. And so when we went and using configurability and customization, we were able to then implement the AI controller, the vector processor, and the data movement engine. So with the AI controller companion core, vector extended up to 2K bits, with the option to add in the AI-specific acceleration instructions and the broad AI data types, as well as additional vector multi-bank memory with a custom interface for improved lower latency, as well as improved data movement in and out the core. And this core can be configured for simultaneous multi-threading, so for threading for execution, as well as separate threading for resource management, interrupt tasks, depending upon what the customer needs. And then going to the AI vector processing element, this is the vector computation beast, where this is now configurable up to 4K bits for VLAN, and also the internal data path is 4K bits as well. So very clean architecture of pulling data in. The interfaces are 4K as well, so pulling the data in through the data path into the execution units and then back out again. All using tightly coupled memories, so fully cycled deterministic, and multiple high-band connection interfaces with a custom DMA interface into the closely coupled memories for pushing the data in for that use model. And then the data movement engine, this is a stripped down version of the 1000 series, so very wide data in VLAN and DLAN with multiple high bandwidth and multiple vector load stores, so that'll give you multiple channel capability. And so under software control, you can be moving data in and out, as well as the option to add AI data manipulation operations. So as you're moving the data, you can also be performing data operations on that data as it moves. And just to say, these cores are all real, they're available, customers are available to start evaluating that. And last year in the RISC-V Summit at Santa Clara, we actually showed a demo of a 2K bit vector core with AI acceleration running some, I think it was the tensor library routines. And we showed that demonstration running on I think it was a Cadence Palladium box over the cloud. So I've gone through the general compute and the AI computation arrays and the solutions that Akeana offers in terms of the processing elements as well as data movement. Now I'm going to go through and talk a little bit about some of the connectivity options that we have. As I said, we have non-coherent and coherent fabric arrays that allow to build out multi-cores, but we've also developed and optimized what we call the AI computation cluster, because clearly we see the need for specific areas of compute. Customers want to pull in cores, accelerators, and so forth, and share the data across these to give really optimum compute. So our AI computation cluster allows customers to build up these computation subsystems. They can be built up to 8 computational units. They have a shared memory, which is a banked shared memory, has multiple interfaces coming in. These can be ultra wide, up to 4K bits, to give very high throughput. And this really enables all the cores, the hardware accelerators, and so forth, to operate in parallel with optimum efficiency and very high data bandwidth. So you can add in the Akeana 1000-based cores. You can also add in a matrix engine, or a customer can bring in their own hardware accelerator block and hook it up into this AI computation cluster, as well as we can have partners, and we're working with partners who have specific compute solutions. They drop this into the AI computation cluster to give this broad range of compute. So following on from the AI computation cluster and looking at the various different types of cores that can be connected up, running in parallel with the shared memory. So we have the Akeana 1000 base cores. They're software programmable. They give you a broader range of flexibility, some more flexible than others. Long vector data computation, control operations, but their tops per watt is not as efficient, but they give you that flexibility. And then you can marry that up with other accelerators. So drop in the matrix engine, which is highly efficient for matrix multiply, very high tops per watt for a specific task. So that task can then be offloaded to that matrix engine and be computing in parallel. Customers can also drop in their own hardware accelerators, their own computation blocks that can sit in the cluster, AI cluster, operate in parallel. And we will work with customers on the integration of these hardware accelerators, work with the parallel operation to gain the maximum compute, data movement, and so forth. But we also have, and we work with partners. And I show you one example of a partner that we are working with, GSI Technology, who have a very interesting optimized implementation for AI computation. It's got a broad range, but in this specific example, we're looking at the implementation of ternary weights, and they give a very optimal performance. So with ternary weights, -1 to 1 bits, they give a very high performance of 10 tops per watts. And that's that combination with all of the other cores allows the partitioning of specific algorithms to compute elements to give a very high computation per watt solution. Okay, so let's explore a specific use case we had when we worked with our partner GSI Technology. And for this, we really wanted to implement a subsystem that was most efficient in compute and gave the highest tops per watt. So we took an inference application, a YOLO model, and initially across all of the different layers, we implemented various different precision formats data types. And the implementation was kind of driven by the smallest size that we could use, but still giving us the accuracy and the precision that we needed. And then once we'd made these updates, we could then implement these on a heterogeneous subsystem with multiple different compute units that were specifically optimized for those sort of different precision formats and data types. So the GSI Technology computing memory bit processing engine is really optimized for ternary weights. So all of the layers that we could actually implement using ternary weights, those running on that GSI core. And with the ternary weights, if you look at the table at the bottom right, that was a white paper published by a hyperscaler, you can see we did not lose accuracy, but with the latency is greatly reduced and memory bandwidth and memory size requirements are greatly reduced, giving us lower power. And then for different layers, different data types, we have the Akeana GEMM engine for those computation needs. And then we also implemented an Akeana 1000 core. It's kind of like a bit processing. Front end and back end gives a broader range of data types, which has the net result that you can take the GEMM engine and the GSI technology core, and adding in the Akeana 1000, you can open it up to more applications, more use models, and you can also kind of future-proof this solution by giving a more flexible front end and back end. And by implementing this, Akeana and its partner GSI Technology can really offer a very optimized highest TOPS per watt compute subsystem. Okay, so now I'll hand over to my colleague, David Baker.
Thanks, Graham. Hello, everyone. My name is David Baker. I'm the machine learning architect here at Akeana, and today I'd like to share with you a little bit more depth in what we've been up to. So it says optimize for local data sharing, and that's really important. We know from AI that memory bandwidth is the key limiting factor for anything you're going to do. We all know that you can outcompute any memory local bandwidth that you can possibly come up with. And so the key point here is that we're trying to balance compute with memory bandwidth. And we want to take advantage of the fact that there's a lot of data locality within a shard between processing nonlinear functions and linear functions. You see that in our CCB cluster architecture. So CCB stands for Compute Coherence Block, and this is one of the IP blocks that we offer. This block is the memory subsystem for processor cores and accelerators that are coupled together tightly and used, pardon the pun, in a coherent way. So the CCB contains both a coherent L2 cache shared by all of the cores in that cluster and the AI accelerators, and it also includes a shared SRAM block. This block is multi-banked, non-tagged, and used to hold transient data that is kind of touch once and doesn't really benefit much from cache coherency. And that's particularly true for data that's produced by the matrix multiply engine and about to be used by the vector engine. Vice versa, when the vector engine is punching out activations, they're about to be used in a matmul operator, and we try to keep all of that together in pipelined organizations that we do for AI processing. Now let's take a deeper dive into the processing elements that are in here. Let's look at the processors, the vector processors themselves. So they have the classic scalar ALU and vector ALU you would expect. They have the scalar reg file and vector reg file you would expect. Now we've added some very significant AI acceleration in this core, and we'll tell you about that on a subsequent slide. But for now I want to focus on data movement. So there is this L1 iCache, L1 Dcache here, but there's also a block called VCCM. This is the vector closely coupled memory, very reminiscent of the DCCM that you find on the scalar side. This block of SRAM is untagged. It's local data memory closely coupled, and it is multi-banked. So we use it in ping-pong fashion between the vector load store unit and the outside world. So on one side of the multi-bank memory, we're doing loads and stores in half of it, and then we ping-pong and do our loads and stores in the other half. Meanwhile, we have this data movement engine, this DME, whose job is to manage the outflow of data from the finished ping-pong side and the pre-positioning of data on the input side. One of the things we know about AI processing is that at compile time, we know when we're building the compute graph exactly which piece of data is going to be needed by which processor in the system or which matmul in the system at compile time. So we can pre-position data wherever it's needed before we actually kick off that computation. And we certainly do that here with the DME engine. So the DME can move data in and out of the L2 cache, or it can move and L1 caches, or it can move data in and out of the shared SRAM. Now that shared SRAM itself is multi-banked and has a data movement engine suite associated with it, so we can move data back and forth between shared SRAMs within the system in a non-coherent kind of way. But there's always opportunities for new algorithms to come along that benefit from coherent memory systems, and so we provide for that. And in particular, some softmax things really benefit from coherent sharing. So we also use that path extensively with the vector processor. We use this as a pull model, a prefetch model, to support loading the VCCM. We can also pull from completely outside the cluster, including off-chip, to get the data we need to process. This is particularly important when we're going after weights and things like that. The shared SRAM is a nice software cache for storing weights that we're going to reuse as we go along. We want to provide instant access to our customers for all of this performance. So Akeana offers an AI performance library implementing the full vector utilization and also the available relevant AI acceleration instructions. So we have AI nonlinear acceleration instructions which provide greater than 10x performance increase for FP16 in such examples as sigmoid and GELU and TAN and exponential. These accelerants are very key to the AI world. So for example, we can benefit from a lower core count. By that I mean when we try to balance the performance of vector processors against high-performance matmul engines, we find that it takes multiple processors to keep up using the standard RISC-V vector instructions. But if we add our acceleration instructions, we can get by with far fewer processors. And that is a dramatic reduction in both area and power consumed for a balanced workload. We also offer our data movement processor for statistics collectives. This is for things like softmax and layer norm. Since it's a RISC-V processor, even though it has limited vector ALU capability, it has enough to support softmax and layer norm as they move data around the ring of processors. So the accuracy for some of the performance kernels that we've accelerated are shown below, and you can see from these dual plots that we haven't taken shortcuts in implementing the accelerations. Okay, let's take a deeper dive into our vector extension pipeline. So we implement the RISC-V Vector 1.0 ISA, supporting the RVA23 profile. How do I know that? Well, one way I know that is that we ran the Synopsys Empress test suite for that, and we passed 100% on our first try. So functionally, we know we are RISC-V ISA and RVA23 profile supporting. We offer vector execution that runs in parallel with a scalar pipeline execution as expected. We offer the standard data types in the vector pipeline from int8 to int64 and then FP16 to FP64. And then we offer a bunch of AI unique and specific data types, including BF16 and most importantly, the OCP-MX formats as well. Now we have another chart coming up that will show you what formats are for both the vector processor and the matmul core. Our vector cores are customizable up to 4096-bit vector lengths. And we also support single or dual vector load store units with strided loads and stores, scatters, and gathers. These are very important operators to AI kernel developers, and we found them also to be useful for vector quantization activities that we've done. We also offer a high-performance vector closely coupled memory subsystem to avoid cache misses and to support software caching of touch-once data objects. We augment that with a custom and very tightly coupled data movement engine in the core itself. In addition, we offer data movement optimized vector core for accelerating the statistics collection and normalization aspects of both softmax and layer norm operators. We measured the value of the large VLAN vector core specifically on softmax, as shown in the graph on the right. The x-axis reflects the inner dimension of various length as reflected in BERT. At the base level, or 512 data elements, at the large level, or 1024 data elements, and at the extra large level, or 2048 data elements. We hand-tuned these softmax kernels for 512-bit hardware and for 2048-bit hardware. We then computed the speedup for the large vector widths, and for the smaller dimension of 512 data elements, we see at least a 2-to-1 speedup. For the largest one at 2048 data elements, we see a speedup of almost 4-to-1, which is nearly the theoretical maximum. Now, softmax is an essential function for neural networks for multi-class classification tasks. It enables models to make probabilistic predictions. The operator has multiple computations. First of all, it computes the exponential for each data element, sometimes twice. So accelerating exponential calculations as we do yields much higher performance. Next, the operator must collect statistics for all the data elements in its input. For SPMD parallelization, this means lots of communication between processors. Our data movement processors are optimized to both collect the statistics across all of the input data elements and then share that result with all the other processors. Finally, we must multiply every single data element by the freshly computed normalization value. And we have shown how our wide vector processor accelerates this kind of operator. All of this is so softmax can yield a probability density function for the classes under consideration. As we have shown you for softmax, we offer the best speedup in all categories, from our greater than 10x speedup in exponential computations to enhanced data movement architectures, and all supported by very wide vector processors. So we offer GEMM systolic array IP. This is a weight stationary architecture implementing matrix multiplication, or in BLAST terms, a GEMM hardware engine. The systolic array is configurable in size and data type and supports 32 by 32 BF16 or FP16 formats as inputs in a 1024 per Mac per clock configuration. At 2 GHz, this is 4 teraflops per second per GEMM. We also offer 64 by 64 MX FP weights in a 4096 Mac per clock configuration, and at 2 GHz this is 16 teraflops per second per GEMM. And finally, we offer a configuration that's 64 by 64 int 8 or 4096 Macs per clock, but we can run the clock a bit faster since the floating point pipeline is gone. This yields out 32 top per second per GEMM. The systolic array itself is tuned for integer math, so we can do this shorter pipeline. So if we look at the block diagram on the left, we see that we are connected to the L2 and NOC. This is to the CCB. There is read flow on the left and write flow on the right. So we're reading weights and activations in any of a number of formats, and you'll see those in the next page, in the next slide. We go into a big systolic array, and that's where these 1024 or 4096 multiply adds occur. We go into the rotail units, and this is where accumulation happens. The accumulators are in the answer buffer. The answer buffer is much bigger than the systolic array, so it's 32 by 512. And this allows us to have ultra-high utilization of the systolic array. So our 32 by 32, this is greater than 95% utilization of the bus. So again, back to memory bandwidth. The 32 by 512 answer buffer gives us this 95% utilization. We support the broadest range of AI data types out there for both our vector processor and our matrix engine. So if we look at integers for starters, int64 and int32 both supported in the vector ALU. int32 output only is supported from the integer GEMM engine. int16, int8, scalar and vector unit support, input and output for the integer matrix engine. Standard FPs, 32 and 64 and 16, we support those on the scalar and the vector, ALU both. On the matrix engine, we don't support FP64 at all. We have FP32 output only, and we have FP16 input and output. As we roll into the AI-specific formats, we have BF16 supported in the vector core, and we have input and output supported in the matrix engine. TF32 and the core, we support it for conversion on input, and matrix engine takes it as input only. FP8, both formats, we have conversion on input in the vector engine, and we have input only in the matrix engine. And then we get into the block data representation. So MX FP8, both formats are conversion on input to the vector engine and input only on the matrix engine. Similarly, MX FP6 is conversion on input to vectors and input only on matrix. And MX FP4 and MX int8 block data representations are conversion on input on the vector side and input only on the matrix side. So with that, I'm going to pass it back to you, Graham.
Okay, thanks, Dave. So it's been a full webinar. There's been a lot of information, and I just wanted to finish off by summarizing what we have at Akeana for the AI compute and data solutions. So looking at the general purpose compute array, we have the Akeana 5000 series core, which is out of order processor, which is industry leading in terms of industry standard with a 25 spec in score. And then in-order cores for the AI accelerated compute area. So we took Akeana 1000 series, and then by customization, we're able to build 3 different types of AI optimized compute engines, the AI control, the vector processor, and the data movement engine. And then in order to further accelerate the performance of some key algorithms for AI, we implemented a greater than 10x acceleration for nonlinear functions, but also a key computation area for softmax acceleration. We could then further accelerate without very wide vector lengths, as well as the data movement engines to give very high performance. As well as the computation cores, we offer a hardware accelerator module. So matrix computation is around 50% of the compute load. So that can be offloaded to the AI matrix engine, our GEMM engine, and that gives a very high TOPS computation. But the systolic array implementation that's been done at Akeana is very optimal. It gives a greater than 95% utilization of the MAC units. As well as offering these, we also have a very robust and flexible implementation of customers bringing in their hardware accelerators. So they can integrate them into the AI compute cluster. They can also connect them up to our interconnect fabrics. And then along lines with that, we are also working with multiple partners who we believe, working with them, we can really bring leading edge performance, TOPS per watt, efficiency for various different parts or layers within a neural network model. And then all of this is supported with our subsystem fabric and memory architectures. So we have like the AI cluster that has a shared memory that you can then bring in up to 8 cores. We also have the coherent and non-coherent fabrics that for the processors, the compute subsystem, you can then connect with also the system IP blocks. And then also this is a RISC-V, so all of these cores run under a single RISC-V ISA, so it's all unified under that single ISA. We support our customers with AI performance libraries, so all of the routines to get these acceleration, to get the data movement engines, the vectorization, these are implemented in highly optimized performance libraries. And then as part of the RISC-V, Akeana is a very active member of the ecosystem and a member of RISE. Okay, so that's all that we have for this webinar. And now I think I'll hand it back to Colleen for any questions.
Excellent. Thank you, David and Graham, for a fantastic presentation. To our audience, we're now moving on to the question and answer portion of the event. So if you haven't done so already, please go ahead and enter your question now into the Q&A text area and hit that submit button. Please note that we will get to as many questions as we can in the time we have left today. If we don't get to your individual questions, someone will get back to you after the program is over. Okay, gentlemen, so we've got several questions coming in here. I'm going to go ahead and get started. Our first question asks, you described the software stack briefly. Can you expand on readiness and what types of use cases are supported?
Hi, Colleen, this is Graham. I'll take this one. So talking about the software stack in terms of the readiness and the types of use cases. So let's first of all look at the compiler level. I mean, we support, obviously it's open source, we support all of the open source compilers. We also are working with a partner, MBEXM, and really optimizing the compiler to our hardware interfaces. And we make available this compiler to our customers. We also have a performance library, which I think we went through in the presentation. This is a library, low-level library that's key AI functions that are highly optimized for performance to our hardware implementation. And these are, again, are available to customers. When we look at, for example, if we look at the general purpose compute array, which we talked about, we run Linux OS, as well as all of the hundreds of applications. We've optimized those to our hardware. And for example, these are database, web serving, virtualization, scientific sort of applications. And we work with our customers to make those available. And also we use those in terms of all of these, the software platform, the OS in our regression, so give high quality IP. And then when we look at the AI accelerated compute array, our tool chain is based around PyTorch to MLIR to IIE down to LLVM. And typically we do optimize this and we'll work with customers in terms of their needs, in terms of the performance that they want to achieve. So this is kind of a collaborative effort in order to get the performance on this full software stack.
Awesome. Thank you very much, Graham. Next question asks, why do you not tightly couple your GEMM engine via a vector register port to your core?
Hey, thanks, Colleen. This is Dave. I'll take that one. So an attached matmul implementation suffer from those exact attachments to the vector register file, ensuring an architectural correctness on the state of the register file. These are all wasted gates and do not compute anything. Both attached AI accelerators and accelerator coprocessors share very significant utilization penalties due to time sharing the rest of the core. Assuming that activation algorithms run in the vector core and linear operators run in the accelerator, then the core is either computing activation or it's multiplying matrices with some small degree of overlap, but in most cases it cannot do both at the same time. Thus, either nonlinear operator hardware is idled while performing linear, or linear operator hardware is idled while performing nonlinear. This leads to low utilization of both computational elements. In addition, we know that the preponderance of flops in an inference are in matrix multiply, and thus we strive for near 100% utilization in our matmul accelerator. This drives us to make it asynchronous to the program stream. Whether the core is performing nonlinear operations or executing interrupt code, we want the matmul operations to move ahead. We achieve nearly 100% utilization with our systolic array that is not interlocked with the register file. Now, while we've taken this approach with our own GEMM, we recognize our customers may have different integration requirements for their own accelerators, and that they would like to attach our cores, and exposing a tightly coupled vector register port along with custom instructions to drive the accelerator is something we can enable. We are aware, for example, that RISC-V International is working on extensions for MATMUL acceleration ports, and as these get ratified, we will support them. Thank you.
Well, thank you, David. Thank you for that. Okay, next question here. We've got several to get through, so I'm going to try to move quickly here. You mentioned multi-threading in your AI core. Can you say more about how this is used?
Okay, Colleen, hi, this is Graham. I'll take this one. So multi-threading, yeah. So traditionally, multi-threading has kind of had a limited use case, especially, focused more sort of networking applications. But when we've been engaging with customers, and Akeana, I mean, the background of Akeana is the engineering team developed the multi-threaded ARM architecture and implemented that in the ThunderX. So there's an incredibly strong technical capability within the company. And we do offer multi-threading, 2 threads up to 4 threads. And in some of the discussions in the for AI compute, the request has come up for multi-threading. And it's more, I'd say it's more in line with, say, the out-of-order cores, less for the sort of AI compute data where you need sort of more cycle deterministic operation. But in those use cases, then multi-threading comes up, as I think I said in the webinar, you've got maybe possibly multiple execution threads, but then also resource management, separate threads for that, as well as interrupts and so forth. And so customers are looking at exploring, and I'd say it's at the stage of exploring, but the benefits of multi-threading. And with Akeana, we offer that capability. It's very mature. We have a very strong team technically supporting that, and we can configure that into the cores.
Excellent. Thank you, Graham. All right, I'm quickly moving along here. In some of the slides, you talked about clusters. Are these clusters built by Akeana?
Okay, it's Graham again, Colleen. Yeah, I'll take this one. So a very simple answer is yes. We kind of build all of the IP that you've seen in this webinar, Akeana builds. We had what we called a CCB, which is a cluster compute block that's for our general purpose cores. This can provide up to 8 cores connected into a single cluster, all coherent in operation. And then that has been optimized for AI because we recognize the requirements, the data movement, the very wide interfaces of the cluster for AI compute. Again, that's 8 cores. We provide that. Customers can configure it to their specific requirements, the number of cores, the width, the size of the memories, the number of banks, and so forth, and if they want caching as well. That can be configured with the customer. We will deliver that and deliver that as an IP block. We also, in terms of just following up from clusters, we also talked a little bit about our coherent 2D mesh under the Akeana Mesh brand. That is, if you want to go to a much bigger core count, fully coherent connectivity, fabric array for multi-cores, we also develop that and we'll also deliver that to our customers.
Thank you, Graham. It looks like I can squeeze one more question in. So to our audience, if we didn't get to your individual question, someone will get back to you after the program is over. So let me see if I can get one more in here, sir. Both of you gentlemen, what kind of simulation capabilities do you enable for your cores, and how can a customer quickly ramp up with Akeana IP?
Okay, it's Graham again. I'll do this one, the last one. Okay. So kind of simulation capabilities and ramping up on the IP. So there's kind of 2 parts. So yes, we have customers who are doing a simulation environment of their SoC. This is generally a System C model. So we offer System C models, whether it's cycle accurate or cycle approximate. We can offer those models of the core, the specific configuration that they have implemented. We also offer the instruction set simulator, the QEMU models that support the cores. We do also have a simulation environment of the QEMU models as well as our GEMM engines, so customers can quickly come up to speed and get those running. Obviously, it's IP. We offer RTL models of the cores. But then for emulation to get up and running, we offer very broad. We Xilinx VC118, I think Pro FPGA, Siemens Pro FPGA, Synopsys HAPS, and Cadence Palladium, which we show both of those in the RISC-V Summit. And that's an emulation platform that we support. So we will offer the bit files. Customers can very quickly have multi-core solutions, the cores, the accelerators, and all of the cluster connectivity delivered to them and then running on HAPS or Cadence Palladium.
Excellent. Well, thank you, Graham, for sneaking in that last question. To our audience, for more information related to today's webinar, please visit any of the resource links available in your green folder icon at the bottom of your screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. So thank you for attending today's webinar, Leveraging RISC-V as a Unified Heterogeneous Hardware and Software Platform for Next-Gen AI Chips. Brought to you by Tech Online, Akeana. This webinar is copyright 2025 by AspenCore. The presentation materials are owned by or copyright by Tech Online and Akeana. The individual speakers are solely responsible for their content and opinion. On behalf of our guests, Akeana, I'm Colleen Heckman. Thank you, and we hope you have a great day.